Welcome to lecture number 5 of the wireless communication course. Today we will talk about performance of communication systems over wireless channels, in particular over narrowband fading channels. Before we do that, it's maybe good to recap where we are in the course. So as you remember from the first lecture, this course had 4 parts. The first part was dealing with the wireless channel and the properties of the wireless channel. The second part on communication performance and optimization over the wireless channel, and then third part about OFDM, multi-user and MIMO communication, and then the last part about more advanced topics such as 5G and radio localization. So I am happy to let you know that we now finished the first part and we go on now to this second part in this lecture and the next 2 lectures. So this will be the topics for today. I will talk about modulation formats and different error probability metrics, as well as a short discussion about differential encoding and detection. Let me first start my timer so I don't go too crazy over time. Good. The material for today can be found in the textbook in chapter 6, where I suggest that you read every section except the highlighted sections here. Learning outcomes for today are the distinction between different types of SNR, computing outage probabilities, average error probabilities, describe the difference between coherent and differential detection, and explain why a differential PSK has an error floor. We will cover all of this today. First, we have a few slides recap from the previous lecture. We've seen that the channel has different components. Let me see my laser pointer here. Right, we've seen that the channel has 3 components: path loss, shadowing, and multipath. They vary over time and they have a specific autocorrelation, specifically for the multipath. Shadowing and multipath are random and they have a specific distribution. So shadowing has a log normal distribution and the multipath has a complex Gaussian distribution, which translates to a Rayleigh envelope and a exponential power. The way that you could generate the channel would be through the step delay line model, where you have different delays. Typically, the difference between those delays would be constant. And then at each delay, you will have a channel that changes over time. And the power of this channel depends on the power delay profile at that delay. And how quickly it changes over time depends on the autocorrelation function corresponding to that delay. We've seen that the channel mathematically has 2 parameters, tau and t. We can then take a Fourier transform with respect to the first one. This gives us f and t. And this is what is shown here. So each of the columns of this figure, like each column here, corresponds to one channel response at a certain time. Right? And then as I change time, we will have different of the columns here. How quickly the channel changes over time depends on the coherence time. How quickly the channel changes in the frequency domain depends on the coherence bandwidth. To compute each of these, we've used these autocorrelation functions. So we've seen this basic autocorrelation function here, from which we can compute the power delay profile. It tells us how the energy is distributed in the delay domain. We can compute the Fourier transform, which tells us the autocorrelation function as a function of differences in frequencies, which tells us the coherence bandwidth. We can compute different Fourier transform pairs. So we have, for instance, in this function, the autocorrelation function is a function of delta t, which tells us the coherence time. And this was the same function that we've seen in the lecture on narrowband fading. We also have this Doppler power spectrum, the scattering function, and all of these are related by different Fourier transforms. And you should be able to interpret all of these, go from one to the other, and derive all of these important quantities such as delay spread, coherence time, coherence bandwidth, and Doppler spread. Good. There's a difference between the channel and how we communicate over the channel. So the channel is given by nature and to some extent also on the carrier frequency. The carrier frequency tells us how quickly the channel varies in time. And then once we communicate over this channel, we choose a certain communication bandwidth, and that then changes the properties of the communication. We have this general autocorrelation function that depends only on 2 arguments because we made these assumptions of wide sense stationarity and uncorrelated scattering. From this autocorrelation function, we can set delta t to 0, and then we can plot this power delay profile, and the delays for which this goes close to 0 is known as the delay spread. We can take the Fourier transform, so let's see. This is by doing the Fourier transform with respect to tau, we obtain this other autocorrelation function. That tells us to what extent two frequencies are correlated, and when this correlation goes to 0, this tells us what is the coherence bandwidth. And delay spread and coherence bandwidth are each other's inverse. We can also have this autocorrelation function as a function of delta t, right, where we figure out when there's a zero crossing or close to zero crossing. This tells us the coherence time. We can compute the Fourier transform of this. This gives us the power spectral density. When this is close to 0, that tells us the Doppler spread. Doppler spread and coherence time are each other's inverse. Right, so again, there's a Fourier transform here with respect to delta t, and in the other direction with respect to delta f, and here with respect to rho. Okay, so that's also mentioned here, and this tells us again this is reciprocal relationships. Good, so this is determined by nature and the carrier frequency that we chose. Once we've chosen a communication bandwidth, then we can relate the bandwidth and the inverse of the bandwidth, which is the symbol slot duration, to this delay spread, coherence bandwidth, coherence time, and Doppler spread. And then we recall that communication is flat, so that means there's no intersymbol interference when the bandwidth is much less than the coherence bandwidth, or the symbol slot duration is much larger than the delay spread. Okay, and this is also known as narrow band or frequency flat. Okay, the communication is dispersive when this is not true, so then you have intersymbol interference when the bandwidth is larger than the coherence bandwidth, or the delay is larger than, the symbol slot duration is larger than the delay spread, and this is wideband communication. On the other hand, we have fast and slow communication. Fast communication means that different symbols see different channels, so the channel changes relatively quickly. This happens when the symbol duration is on the order of the coherence time, or the bandwidth is on the order of the Doppler spread. On the other hand, we have slow communication when the channel is constant for many symbols, and then this corresponds to the symbol slot duration being much smaller than the coherence time, or the bandwidth being much larger than the Doppler spread. We've also seen how to simulate a wideband channel, right? So the way that you do this is you decide a communication bandwidth, you have a delay spread that you've computed from your autocorrelation function. So this delay spread, this guy, these are all computed from AC tau delta t. You have total received power. You then determine a number of channel taps that are equally spaced, one over the bandwidth, one over double of the bandwidth, to span the entire delay profile. For each of the taps, you choose a variance, right? And the choice for this variance depends on the power delay profile, right? So the power delay profile looks like this, and then for each of the delays, right, so each of them is spaced 1 over 2b apart. Each of the delays you have a value here, and this gives you a variance, sigma squared, for the ith path. A typical profile is an exponentially decaying profile. We need to make sure that the total power is preserved, that we don't inject more power, and that we do this by this constraint. Once we have the variance for each tap, then we can generate complex Gaussian random variables according to that variance with zero mean. Okay, this is for Rayleigh fading, so the mean is 0. If we have Ricean fading, then this mean will not be 0. It will depend on the line of sight path. When we generate in step 3 these complex variables, we can do this with a rand_n function. This will be then giving us IID complex random variables. Now, these would vary very quickly. In order to properly model the time evolution at this corresponding delay as a function of delta t, we should use a filter. And this filter will be discussed in the project. Good, so this was a recap. So now we go on to the topic of today. I should mention one thing. I'll write it here. So before we've seen the notation gamma for the path loss exponent, right? Here, gamma will also be used to denote SNR. So it's an unfortunate fact that the notation is used double, but yeah, so here it will only be for SNR, not for the path loss exponent. All right, so now we will look at how to evaluate communication performance. We start from our general complex baseband signal, so U of t, which we now explicitly write as a sequence of symbols with a certain pulse shape and a certain symbol slot duration. So again, Ts is approximately 1 over b, depending on whether or not the pulse has a roll-off. The received signal in an additive wide Gaussian noise channel would be the transmitted signal plus noise, and this noise has a power spectral density n0 over 2 for the real and imaginary dimension. At the receiver side, after match filtering and synchronization and sampling, we'll have these kind of observations. So yk is the square root of Es, where Es is the energy per symbol. Ak is the symbol drawn from the constellation plus noise. And in this model, we can compute the signal-to-noise ratio. There are two versions. One is the analog version based on the analog waveform. So it's the received power over the noise power. So it's the received power over the noise power spectral density times the bandwidth. It's given by this. There's also the digital version based on this expression, which is the energy per symbol over n0. And you can easily relate both to each other, since the symbol duration is typically 1 over b, so they're actually the same thing. As we've seen in the first lecture, there are two notions of SNR, SNR per bit and SNR per symbol, where each symbol carries a number of bits, right? So if you have an 8-point constellation, each symbol carries 3 bits. Gamma S will denote the SNR per symbol, so Es over N0. Gamma B is the SNR per bit, so it's the SNR per symbol divided by the number of bits per symbol. With this, we can evaluate different performance metrics, such as the symbol error rate or the bit error rate. So this is the probability of making a mistake on the transmitted symbols AK, and the bit error rate is the probability of making mistakes on the bits in these symbols. And as I mentioned, yeah, gamma is used for two things in this lecture. Good, so here we have an example of MPSK, so this is here 8PSK. It turns out that for some constellations like MPSK, the symbol error rate, so this is here, the symbol error rate has an approximate closed form expression given by this. Oh, this doesn't look very nice. Given by this, so depending on the value of m, how many points there are in the constellation, we have these expressions for the symbol error rate, and these are approximate. Well, actually, for m equal to 2 and 4, they're exact, but for m greater than 4, it's an approximation. Similarly, for any PSK, any QAM constellation, we have this expression for the symbol error rate, again as an approximation, typically tied at high SNR, where you have these constants that you can find in tables. If you want to compute the bit error rate, which we denote here by PB, bit error rate, under gray coding, you can relate one to the other just by dividing by the number of bits per symbol. Gray coding means that consecutive symbols have only one bit difference. So it could be like this, 0, 0, 1, and so forth. So there's only one bit different going from one symbol to the next. So if you would have, for instance, here 1, 1, 1, 1, 0, 0, this would not be gray coding, because here they differ 2 bits, while they should only differ 1 bit. We will use the Q function a lot, and this is given by MATLAB by this standard built-in Q function. Good. Now, the expression that I showed here, right? So you have this alpha and beta, and in this slide, which I just copied from the book, you find the values for alpha and beta for many constellations. So you don't need to memorize this. If we ever use this, you will given these expressions. Good, so this was for the additive wide Gaussian noise channel. Now we have the flat fading channel here. So what differs is that we kind of multiply the signal with the channel. And then based on this, we have different ways of measuring performance. And actually now it's time for a break, so I will take a break and then we resume after the break.